Okay, so this is part three of the slides for confidence intervals. In part two, we talked about how we find the z multiplier, the basis for the way the confidence interval is constructed the way it is. And we also talked about how we could use R to find the multipliers for any confidence interval. So one of the things that we left off with is this idea that the formula, right? X bar plus or minus z1 minus alpha over 2 times sigma over square root of n is based on the population variance, which is a value that is unknown. So what do we then do? And right, so the idea that most of you probably think is, well, let's use the sample standard deviation instead. And that's what we'll be doing. And we'll talk about how this fact changes the confidence interval a little bit. So recall a few things. Population variance sigma squared given by this equation over here. So uppercase N represents the population size. Sample variance is given by this equation over here divided by N minus 1. So when sigma is unknown, we'll use the sample standard deviation to estimate. Right, so remember that variance is the squared of the standard deviation. So previously, right, we computed the standard deviation of the sample mean as sigma over square root of n. When sigma is not known, we compute what we call the standard error of the sample mean. So we replace sigma with s. So when the standard deviation, sigma, is estimated from the data, right, we call it the resulting result as the standard error of the statistic. So the term standard error usually implies that in the calculation of the standard error, we have a sample quantity over here instead of the population quantity. And in reality, right, we are going to be calculating standard errors a lot more than standard deviations, right? Because standard errors use the sample quantities, which are actually values that we do have, so we can calculate a numerical value. So let's think about some of the things that we talked about, right? We say that if sigma is known, your sample means, right, follow a normal distribution under some circumstances, and one can standardize, right, this x bar by subtracting the mean and divide it by sigma over square root n to find your z distribution, which is a standard normal with mean 0, standard deviation 1, right? So basically, this quantity over here follows a standard normal distribution. When sigma is unknown and estimated using sample standard deviation, the distribution, right, that we are looking at is now of x bar minus mu over s over n rather than sigma over n. This quantity over here is approximated by something that's not really a standard normal distribution, but a t distribution with degrees of freedom given by n minus 1. So we are now looking at a t distribution instead of a standard normal distribution. If our population was originally not normal, then the approximation to the t distribution works well if you have a large sample size. So, right, basically we're saying, right, under some circumstances, this quantity over here will follow a t distribution instead of a standard normal distribution. So one thing you noted, right, is that a t distribution is specified by its degree of freedom. Typically, we'll write it as t subscript k, where k represents the degree of freedom. So for the confidence interval for the population mean, the degrees of freedom, which we write as k, is given by n minus 1. It's basically sample size minus 1 because, right, there is one equality that we have to write for this, right, since we're using the sample mean, right, to estimate the population mean, right, we lose 1 degree of freedom because this equality must hold. Now, what's the comparison between a t distribution and a standard normal distribution? Both are centered at 0, symmetric bell shape. So the general shape is still the same. The only differences are t distribution has associated degrees of freedom, and the t distribution has larger spread. So what does this mean? So if I sketch, right, so if blue represents, right, the standard normal, and red represents the t distribution, a t distribution, its curve will probably look a little bit like this, right? So it has a little bit more area in the extreme values. Now, one thing to note, as the sample So maybe to be a little bit more accurate, I should rephrase this as the degrees of freedom increases, the t-distribution approaches the standard normal, right? So basically, from a practical standpoint, it means that if you have a larger sample size, then your t-distribution, this red PDF, will get closer and closer to the blue PDF. So we will use the sample standard deviation to estimate sigma, the population standard deviation, when it's unknown, and that's typically almost all the time. So our confidence interval for the population mean now becomes this. So if we compare equation 3 with equation 2, right? Equation 2 we wrote x bar plus or minus z1 minus alpha over 2 times sigma over square root of n. So notice some of the changes, sigma here, and we are using a t-distribution instead of a z, right? So this t-distribution, again, like the z, right? It's basically, we want, if we draw your bell-shaped curve, right, the area between between the two proportions, the two values over here to be your confidence level, right, 1 minus alpha. So this is the percentile, the value on the t-distribution that's associated with alpha over 2, right, because that's alpha over 2 over here. And that's the t-distribution with percentile 1 minus alpha over 2. And of course, you have to specify the degree of freedom. So how do we find the t multiplier? Instead of using q norm, you're using qt, right? So value of percentile df, right? So for 90% confidence, right, we have alpha equals 0.1. So 1 minus alpha over 2 is now going to be 0.95, right? So for this first one, what we're going to do, we'll type in qt 0.95 comma 10, and this will give you a value of 1.812, right? With 92% confidence interval, confidence level, right, your alpha is 0.08, so your 1 minus alpha over 2, if you work it out, will give you a value of 0.96, right? So to find this second one over here, so let me just differentiate this a little bit better, right? So for this one over here, you will type in qt 0.96 comma 35, and I actually didn't calculate that value. You could work it out on your own. This last one, 98% confidence, alpha is 0.02, so 1 minus alpha over 2 is going to be 0.99. So this last one over here, you will type in qt 0.99 comma 50, right? 50 degrees of freedom, and it's 2.403, right? So a lot of the concepts are the same, right? We're putting the percentile over here. It's just that you're using qt rather than q norm. Let's look at an example of a potential interval that you could calculate. So let's recall, right, that the formula for the interval given over here. So there are a lot of bits and pieces of these pieces of information that we need. Sample mean for 110 randomly selected. So, right, we need a sample size. So we already know sample size is 110. Sample mean is 76.7. So x bar 76.7. Sample standard deviation 12.3. So S is 12.3. Some of the bits and pieces of information, the degrees of freedom K equals sample size minus 1, so it's going to be 109, right, because we know sample size 110. So let's compute this confidence interval over here. So the confidence interval, we're just plugging in all the values that we have. So sample mean, plus and minus. So this t-distribution, you will find it by typing qt. So if it's 95%, then the percentile is 0.975, comma 109, times S, which is 12.3 over square root of sample size. And if you work this out numerically, this should give you the lower bound to be 74.376, upper bound to be 79.024. Right, so we're pretty sure that the true population mean LTDR loan to deposit ratio is between one of these values. So sometimes you might say, is it reasonable to say based on this interval that the average LTDR is less than 80 for the population? Yes, right? Since the entire confidence interval is less than 80, right? So basically the way we interpret this value is that any of these any value within this range is plausible for mu, right? So remember that this represents sample mean. We have no idea what the population mean is. So we say we're pretty sure that the population mean is between these values, and any value, right, is going to be less than 80. So it's reasonable to say that the population average is less than 80.